We're back in Topics with Statics, this time equilibrium in 3 dimensions. This is all very similar to equilibrium in 2 dimensions. The first thing we have to figure out is support reactions. There's a table in your book that shows support reactions for various supports. I'm not going to go through all of those. The big one's ball and socket and a journal bearing. And a ball and socket doesn't produce any moments. It'll produce 3 forces, but no moments, because I can rotate it around that ball and socket. A journal bearing produces forces and moments in 2 directions only. In other words, that shaft is free to slide through the journal bearing, and then it's also free to rotate. So equilibrium in 3 dimensions means I've got 6 equations. Right, I've got sum of the forces, x, y, and z, each have to be 0, and the sum of the moments, my, x, y, and z, also have to be 0. It gets ugly. It's a lot of equations. There's some special cases where I may not need all of those. If all the forces are concurrent at a point, I don't get any moment equations, right? That they don't produce any moments about that point. And so then all I would need would be the sum of the forces to be 0. Right? If all the forces are concurrent with a line, in other words, the line of action of each force passes through the same line, then I get 5 equations. I lose whatever that line is. Here, all these forces pass through the x-axis, so I don't get a moment about the x-axis. So I've only got 5 conditions for equilibrium. If all the forces are parallel, I only get 1 force equation, whatever direction that is. They're all in the x direction. And then I get the 2 moment equations that are perpendicular to that. So moments y and z in this case. Free body diagrams, right? Everything you ever see will tell you to draw the free body diagram. I find this incredibly hard. It's hard for me to draw a picture in 3 dimensions. The temptation is to draw all over the picture that you're given with the problem. Try and resist that temptation. And the reason I want you to resist that temptation is that if you cover up the picture by drawing all over it, then later when you need to go back to that drawing for something, you can't see it. And so try not to draw all over the picture. All right. Dr. Seuss says to assist, make a list. When we start working problems, you'll see that in 3 dimensions, I typically make a list of all the forces. I sit there and draw the free body diagram in my head. I just make a list. Here's all the forces that are acting on that object. And then I write them down as Cartesian vectors. And that list is what I use for my free body diagram. But having said all that, let's try and draw some free body diagrams. Here's a triangular plate. So, triangular plate. Here we go. Okay, there's a triangle. Done pretty good so far. So now what forces are acting on it? At A, it's got a roller support. So I would say there's a force pointing in the y direction. At A. Same thing's true at B. So at B, we've got a BY. All right, I've got a applied load over here. That's my force F. And then it's C. C looks to me like a ball and socket. So I would say it's got a force pointing this way. I labeled every one of those wrong, didn't I? Everything I labeled Y should be a Z. So let's just go back and change that. This is why you don't scribble all over your picture. So this should be CZ. And then it'll also produce X and Y. That looks better. And that should be it. That should be all the forces acting on that object. Let's try again. Since that was so easy, let's try one more time. Maybe I can get my X, Y, and Z correct this time. So I've got some object. It kind of looks like that. So what forces are applied to it? Let's start out here at this elbow. There's a force F. And then I've got 3 journal bearings acting on this thing. And at a journal bearing, I get forces that prevent translation perpendicular to the axis. There's a hole through it, perpendicular to that hole. So in the X and Y directions at A, I'd get X and Y. This is Y. I'm just going to do the forces to begin with. So at B, it runs along the y-axis, so I get forces X and Z. And at C, the axis, the hole through it is in the X direction, so I get Y and Z. And then I get moments in each of those directions also. So I'd get a moment X, a moment Y. That's still bad notation. AX, AY, moment BX, moment BZ, moment CY, and a moment CZ. And that should be all the forces acting on that bad boy. So now we get into a whole another can of worms. Constraints and statical determinancy. Essentially what we're worried about is, how do you know if it's going to be, if the supports you've applied to it are proper to make this thing not move? If you're an engineer, you got to worry about that. A structure that satisfies that requirement is externally statically determinate. Right, I'm calculating all the external reaction forces using only static equilibrium. If I can determine what all those forces have to be for a specific load, then it's externally statically determinate. Some bodies have more supports than are necessary for equilibrium, so I may not have enough equations to calculate all those supports, in which case it would be statically indeterminate. Right, more supports than are necessary are called redundant constraints. That makes it statically indeterminate. There are more unknown loadings on the body than equations of equilibrium. Right, this pipe assembly has 8 unknowns, but I only have 6 equations from static equilibrium. So I can't tell what those forces are going to be. That doesn't mean it's a bad thing. I just can't calculate them. You can also have what are called improper constraints, constraints that do not guarantee that the object's not going to move. Right? A couple of specific cases, if the line of action of all reactive forces intersect a common axis, it can rotate. I get weird rotations in. If all the reactive forces are parallel to each other, again, I could get strange rotations. Fewer reactive forces than equations of equilibrium, right? If I only have 3 support reactions and there's 6 equations, it's not going to be stable. There's no way. We're not going to get into all of that. We'll talk a little bit about it. You'll cover all of that more generally in future engineering classes. Next time, we're going to start structural analysis. In other words, we're going to be getting ready to build bridges. Until then, have fun.